p-values, statistical significance. You see these words thrown around all the time, right? In news about medical breakthroughs, in market research, pretty much everywhere. But today, we're going to pull back the curtain and really get into what they mean and, just as importantly, what they don't. Okay, so let's dive right in with a super simple scenario. Imagine a clinical trial. The people taking a new drug, their blood pressure drops 10 points more than the people taking a sugar pill. So, the million-dollar question is, did the drug actually do that? Or was it just a lucky roll of the dice, a total fluke? How do you even begin to tell the difference? Well, to answer that exact question, scientists and statisticians have a very specific tool in their toolkit. It's called the p-value, and its entire job, its whole reason for existing, is to help us figure out the role that pure random chance might be playing in our results. So what is a p-value? At its heart, it's just a probability, a number between 0 and 1. And it answers a very, very specific question. It asks, let's pretend for a second that our new drug does absolutely nothing. What's the probability we'd still see a 10-point difference just by random luck? You can almost think of it as a flukometer for statistics. Now, to use this tool, statistics sets up the problem in a really interesting, kind of backwards way. It starts from this position of extreme skepticism called the null hypothesis. This basically assumes the drug is useless, that there's no effect, and anything we see is just a coincidence. The other idea, the one we're hoping for, is the alternative hypothesis, that the drug actually works. The p-value is what helps us decide which of these two ideas the data supports more. Okay, so we've got this p-value, this probability that we're just seeing a fluke. But how small does that probability have to be for us to get excited? For us to say, this probably isn't just a random coincidence. Well, statisticians needed a rule, a line in the sand. And for decades, this has been the magic number, 0.05, or 5%. It is by far the most common threshold used in science to make a judgment call. If the probability of your result happening by pure chance is less than this number, well, then you've got something worth talking about. So this is where it all comes together. When your p-value dips below 0.05, we get to use the big phrase, statistically significant. Now, this does not mean it's proven true. It just means it's pretty unlikely to be a random fluke. Think of it this way. The chance of us being fooled by randomness is less than 5 in 100. And that gives us enough confidence to push aside that initial skeptical idea, the null hypothesis, and say, okay, it looks like something real might actually be going on here. Let's make this feel a bit more intuitive. Imagine you grab a coin, you flip it 10 times, and it comes up heads 9 times. I mean, your gut is already telling you something's fishy, right? Well, the math backs you up. The p-value for that is about 0.01. That means if the coin was perfectly fair, an event this lopsided would only happen about 1% of the time. So let's connect the dots. Our p-value, 0.01, is way smaller than our 0.05 threshold. So what does that let us conclude? Well, it means we have statistically significant evidence to believe that coin is not fair. We'd have a really strong reason to suspect it's biased. Now, that coin flip logic, it seems pretty straightforward, doesn't it? But believe it or not, it's right here where some of the biggest and most dangerous misunderstandings in all of science start to creep in. Getting this next part right is absolutely everything. So let's bust some common myths. Okay, these are so important. Let's walk through them. First, a tiny p-value does not mean the effect is huge or important. A drug could have a teeny tiny effect, but if you test it on enough people, you can get a super small p-value. This leads to overhyping really minor findings. Second, significant does not mean 100% true. A less than 5% chance of being a fluke is still a chance. And third, this one is huge. A high p-value does not prove there's no effect. It just means you don't have enough evidence to rule out random chance. This mistake can cause us to give up on promising new ideas way too soon. It's a verdict of not proven false. Big difference. So if you remember just one thing from all of this, let it be this. Statistical significance is not a stamp of truth. It's a statement about probability. All it's saying is, based on the data we have, it's pretty unlikely that we're just being fooled by random noise. That's it. That's the whole game. So, if it's not a finish line, then what is it? What is the proper way to think about a statistically significant result? Let's use one last analogy to pull this all together. Imagine you're watching a friend roll a die. In just 10 throws, they get 7 sixes. You immediately get suspicious. So you do the math and find out the p-value is about 0.015. Since that's way below our 0.05 line, you can say you have significant evidence to suspect the die is loaded. But is it proof? Absolutely not. It's just really strong evidence. It's the justification you need to say, hey, let's take a much closer look at that die. And that just perfectly illustrates the big idea here. Finding a statistically significant result isn't the end of the story. It's not the goal. It is the very beginning of a new investigation. It's a flashing light that tells you, hey, this thing over here is worth a closer look. It's worth more experiments and more scrutiny. And that really brings us to the whole point. What is a p-value for? It's a gatekeeper. It's a filter for our attention. It helps scientists sort through all the random noise out there to find signals that might be real. It doesn't tell them if a discovery is big or important or even if it's true. All it does is tell them if it's interesting enough to open the gate and start a real investigation. And honestly, that's all the difference in the world.